Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, House Robber 4. If you haven't solved the first 3 house robber problems, I would definitely recommend at least solving the first one. I think we've solved 1, 2, and 3 on this channel or the other neat code channel. This problem will definitely be similar, but definitely different. Almost like they're trying to trick us with this question, but let's get into it. The idea is that we're going to be given an array of integers. So in this example, we're given something that looks like this. Like with most of the house robber problems, the idea is that each of these numbers represents a house. We are trying to rob some of these houses. They give us a parameter k. In this example, it is equal to 2. So that means we're trying to rob at least k houses. So at minimum, k houses we want to rob. So in this case, 2 of them. Now, even though they tell us we're robbing a minimum of k houses, after you go through the entire description, it becomes pretty clear that you would probably never want to rob more than k houses in the first place. So you can pretty much just assume that we're robbing k houses. Now, why do I know that? Let me just kind of spoil it for you, just go through the rest of this problem description. We want to rob at least k houses, so from here we want to rob k of them. We do not want to steal from adjacent houses, so if we take this, we cannot take that, so then we maybe take something like this. Okay, so in this case, we've taken exactly 2 houses, and among these k houses, among all of them, we want to take the maximum number among all of these. So they tell us that over here. They say the capability, so that's the key word that they use here, is the maximum amount of money that we steal from one of all of the houses that we robbed from. So aka the maximum among the ones that we actually robbed from. So now you tell me, if we've taken from k houses, and so this is what we have, adding additional houses is never going to make that maximum number any smaller, right? At the very least, you should agree with me on that. So if there is a solution, and there's a solution where we rob exactly k houses, and there's guaranteed to be a way to rob that many, so we'll always know that there at least will be a solution. And so if there is a solution, then adding more houses to it, adding like a third house more than we actually need, more than k, is never going to help. So we don't need to do that. So that's why we can assume that we're only going to take exactly k houses, not at minimum k houses. So anyways, that was kind of a tangent, but I want you to know that those sorts of tangents are very important in solving problems like these. I call it making observations about the problem. It's very important. Don't try to skip this step. So let's get into this. With the main idea out of the way, like what this problem is asking for, it seems pretty difficult because there's so many different ways to rob houses. It's more than just n squared, because n squared would mean like the contiguous subarrays from each element. But with this, we can either choose to rob a house or choose to skip a house. So we have that choice for every single element. So we're going to end up with something like a decision tree where we can choose 2 or skip 2, choose 3 or skip 3, and we kind of just keep going like that, choose 5 or skip 5. And then among each of these paths, it will tell us how much we could rob. So for a given path, this is one possibility. Among all of these values, we will take the maximum, which in this case is 5. And then we'd say, okay, for this path where we robbed at least k houses, 5 was the maximum. And maybe for a different path, something else was the maximum. Among all of those paths, and obviously this would have been an invalid path because we cannot take contiguous houses, so 3 is technically invalid, so sorry about that if that was confusing. But this was mainly just to illustrate the main idea. Among all of these different paths, we want to get the one that has the minimum capability. So if you take the maximum from this group, maximum from that, and for every path, you want to get the one that has the minimum. And for this example, the minimum is going to be the one that has this one and this one. Because if you look at this group, the maximum of this group is going to be 5. If you take any other group that has at least k houses in it, if you take this and this one, it has 9 as the maximum. If you take 2 and 3, it has 3 as the maximum, so you might think that this is better, but this is technically invalid because we cannot have 2 houses that are adjacent to each other. So for that reason, we cannot take this. And so some other possibilities, I guess, is this and this. But again, that also has 9. So I think we pretty much went through all of the valid possibilities at least. So among all of those, 5 was the smallest. So the solution I showed earlier is going to be exponential, 2 to the power of n, but we can use caching, the memoization strategy, to get that down to actually be an n squared solution. I'll quickly show you the code for that, but this solution actually gets memory limit exceeded because it's not very efficient, not just in terms of time, but the space complexity is also n squared. We can get that down by doing a bottom-up solution, but the bottom-up solution will give us time limit exceeded because even though the memory is going to be linear, the space is going to be inefficient. So we're actually going to need a better solution than the one that involves dynamic programming. The good thing is that that solution is actually easier. I'll show you that one in just a couple minutes. So very quickly, let me show you the memory limit exceeded solution. So there might be some spoilers here, but this is the full recursive solution. I added caching to it. I had a couple simple base cases, and then just the choose and not choose recursive steps, and then just minimizing that and then returning it. And then the bottom up solution, which is this code right above it here, is very, very similar to the top-down code. I won't go like super in depth and draw this part out just because it's pretty complicated, and there is a more efficient solution that is also easier that I'm going to show you now. So I feel like I'm obligated to mention that if you're not familiar with binary search, if you're not familiar with Leetcode, definitely check this out. Link will be below. And definitely solve either one of these two problems, Coco eating bananas or capacity to ship packages, because they're very similar to the trick that I'm about to show you right now. And I would probably recommend Coco eating bananas. You can see the solution here in pretty much every language and video explanation as well. So just to tell you what the trick here is, it is binary search. I think you're probably wondering, like, if you haven't seen some of the more recent videos or just any video related to Coco eating bananas, you're probably wondering how that's possible. More importantly, how would you be able to know that this is a binary search problem and not a dynamic programming problem, like we talked about earlier? Well, first of all, it is a dynamic programming problem. So if that's like your solution, there's nothing wrong with that. There's nothing wrong with determining that this is an n squared problem using dynamic programming. For problems like these, it's very hard to arrive at the slightly more optimal solution, which is, in this case, I think going to be n log m. So in some ways, it's not even 100% true that this is always going to be more efficient. In most cases, it definitely is. But yeah, it's hard to come up with these slightly more efficient solutions when you're not really sure. And I'm sure you're wondering, like, how would you be able to come up with this by yourself? That's a very hard question to answer. I think I probably wouldn't really try to if I were you. Just focus on learning the pattern and being able to apply it when you need to in the future. But with all that out of the way, let's think about how we can apply binary search to a problem like this one. The general idea is that, first of all, obviously, we're not actually searching a data structure here. We're not searching for some kind of target. We're not doing anything like that. So the way we apply binary search for problems like these, I call it searching on a range. In my Algorithms for Beginners course, I have that pattern over here under binary search. There's searching an array, and there's also this concept of searching a range of values. And so I'm basically just going to kind of take you through the process of breaking down a problem like this one. First, we want to do binary search on a problem like this one. The general idea is that you can take something like this problem where there is like a step that involves brute forcing something, and we can optimize it by applying binary search. So I'll abbreviate that with BS. And we do that on a range of values. And usually that range is the part that was inefficient here. So it's kind of like a three-step thing. You find like the brute force thing, you optimize it by applying binary search. I don't know if it's actually 3 different steps, but this is how I kind of think of it. So for a problem like this one, it's kind of hard to apply this. We don't even know what our range is. Well, what we're trying to do is find something. We want to return the minimum capability. So probably that's what we're trying to find the answer to. What is the capability, the minimum one? So now I'm thinking of that range already. In some ways, I guess I'm kind of skipping these steps, but I know that for my capability, the smallest the capability could probably be is 1. It's probably never going to be less than that. And usually the setup of this is pretty easy for one of these endpoints. Usually the smaller one is going to be 1. Now, what's the bigger endpoint of this going to be? What's the largest the capability could possibly be? For this problem, it's not super complicated, but it's a little bit subtle. It's not something that's going to be obviously clear to you unless you actually think about it. Well, what is the capability again? That is the maximum amount the robber can steal among all of the houses that they actually chose to steal from. So the maximum that the capability could possibly be is whatever the maximum value is in that array of nums. It can never be bigger than that. So here we can just say that our range is going to be from 1 to the max of nums. So this is the range that we're searching for. So now we have the range at least. And now I guess we're going to do these other two steps. Figure out how we would solve something like this in a brute force way. And then in terms of optimizing it, it's pretty straightforward. We'll just take that brute force approach and instead apply binary search to it. What I mean is that we now have this range of values to search from. We could do it in linear order from 1 to 2 to 3, all the way up until the max number, and we'll stop at whichever one was the largest one that, or I guess in this case, it's the opposite. We're actually going to stop at the smallest one that is valid. But once we do have that stopping point, we're pretty much done. Now, rather than going through those one by one, I guess in this case, we'd be doing it in reverse order. Instead of doing that, we are going to run binary search on this range of values. So now in terms of what's left for us to do here, well, let's think about this. If somebody gave me some capability, let's call it C, and they gave me this array and this input data, how would I determine? Let's have an example for C. Actually, let's do a dry run at this point. So here is my example. And so let's do our setup. So our range initially is going to be from 1 up until the max number, which in this case is 9. So this is our search space. And then we're going to run binary search here. So let's calculate the midway point. And as I do this, you'll probably get an idea of what the brute force and the optimal thing is. So my midway point is going to be 5 in this case. And so that's my capability. To put it into context, this means that, for example, here, if I took this and this, I took K houses from here, and the maximum amount was 5. Thus, the capability here was 5. Now, if I took, let's say, just this house 3, and maybe there was another house over here that's 2. So therefore I did take 2 houses and the maximum one was 3. So that 3 technically in this case, which is the max, is also less than 5. And so 5 would also be valid in this case technically. Even though a more precise value is 3, we would also say that a capability of 5 is technically still valid. And how can we, now given a capability, how can we determine if there are at least K houses in there that are not adjacent to each other? It seems more difficult than it actually is, believe it or not. What I'm saying is, given some arbitrary M value, some capability, how could we know if there are at least K houses from the input that we can choose from where the values of each of those houses is less than or equal to this value? How could we know that? Well, there's not a way to do it in constant time. I'll just tell you that. The way to do it is to do it in linear time, and it's actually pretty easy. All you do is scan through the input and count how many of the values are less than or equal to the capability, in this case, which is 5. Well, now is the part where I'm sure you're noticing, well, there's a potential issue with this counting, and it's that it does not take into account that we're not looking at the adjacent neighboring houses. We do not want to include those because in this example, what we would get is we'd count the 2 and we'd count the 3 and we'd count the 5 because that's also less than our capability. We would not count the 9, we would skip that, but in total, we counted 3 houses. But the reality is we only needed 2 of them, but we counted 3. And with these 3, we wouldn't actually be able to choose all 3 of them. So that's why this is an issue. A simple example to show this would be something like this down here, where maybe I have like a 10 and a 10 that are adjacent to each other. The M value I'm looking at, it might be a 10 and maybe my K is 2. So I'm looking for 2 values that are less than or equal to 10. And if I were to scan through this, I would count 2 of them. I'd count this one and I'd count this one as well. But I don't actually have 2. I can only pick one of these because I can't pick the one that's adjacent to it. So that's the issue, just to make it very clear. Well, the fix for this is honestly very easy. It's almost too easy. So if you weren't able to come up with it, that's probably why. Think of it like this. Imagine if you just have like a line here. Anytime you see like a box, like that's what we're trying to do. We're getting a box. And if we see one, then we jump two spaces. And if we don't see one, then we just jump one space and we just kind of keep going. And if we see maybe two adjacent boxes, that's okay. When we see the first one, we take two jumps. So we would go over there. Now, maybe there's a box here. That's good. If there's not, that's fine as well, because this jump just means that we skipped the one over here. So to like put it in terms of X's and O's maybe is better. If we just have a bunch of X's, and let's say we're trying to count all of the X's that aren't adjacent. Like for example, here we could count this one, and that's what we're trying to do. We can't not count like two adjacent ones of these. The algorithm is basically to pick one and then jump two spots. Now we're here, jump two spots. We're here, we didn't pick anything, so we can jump one spot. We're here, so we take that, we jump one spot here, and kind of just keep going. So we counted 1, 2, 3 X's. Basically, when we were here, we saw that if we want to take this, we want to count this, we are not allowed to count the next one. And that's the only restriction. We can count anything that comes after that. So that's basically the idea behind this algorithm. So for us to be given some arbitrary capability and to determine if it's valid or not, all we have to do is scan through the input array and then count the values, comparing each to that capability itself. And then if our count at the end is greater than or equal to k, then we know that this was valid. And thus we can try to look for an even bigger one. So to briefly finish up the dry run, we saw that 5 was valid. So our range was 1, 9. We will now up our range to be 6 to 9. We would increase the lower bound of the range. And now we're going to try a value that's in the middle of this. 6 plus 9 divided by 2 is 7. So now we would try 7. We would count how many of these are less than or equal to 7. So getting rid of this. We go through all of these and we see only this one is bigger than or equal to 7. So we only counted 1, but we wanted at least 2. So thus 7 was too big. So we're going to make our range smaller now by taking the big number 9 and decreasing it to be 7 minus 1. So it would be 6. And so now our range is just 6. And we would find that 6 is also not valid. So the largest value that we found in the range 1 through 9 that was valid is 5. So that's what we would return here. So the time complexity of this is going to be n, because we're going to have to scan through the input every step of the binary search, and log of m, because if you remember, our range, the size of that is going to be determined by the max value in the input. So that's what my m here is. This is going to be the overall time complexity. I believe the space complexity should be constant. So I'm going to do pretty much a textbook binary search the way I like to code it, at least. So even though I said earlier that our range was going to be 1 up to the maximum of nums, I guess a tighter way to do this would be to take the minimum of the nums as well for our lower bound. I kind of overlooked that when I was talking about it earlier, but we wouldn't expect us to rob less than the minimum house amount. So I think that's why we can do this as well. And then we pretty much just do binary search while left is less than or equal to right. We expect to return within this function, and we expect that there to be a helper function. Let's just call it is valid, and it will be given some capability, and we will determine if that capability is valid for the input or not. So assuming we have a function like that, this becomes very trivial. I'll kind of just show it to you. We can calculate the midway point. So mid is going to be left plus right divided by 2. We don't really worry about overflows for this, but we could if we wanted to. And we also will have our function being called basically. So it's going to be pretty easy from here. So if is valid, given that value m for the capability, if it is valid, then we will update our result to be that value, and then we can update our right pointer to be equal. Actually, this makes me realize I might have misspoken when I was doing the drawing explanation, so sorry about that. I keep forgetting we're trying to return the minimum capability, so every time we determine that this is valid, we are actually now looking for a smaller valid result, so we should actually shrink our range, so we should take our right pointer and set it to be mid minus 1. And in the opposite case, we can set our left pointer to be mid plus 1, because if we find that this is not valid, then we will have to try a bigger capability to see if that's valid. And then at the end, we will return the result, which I have yet to declare. So let me do that somewhere. And we expect that the isValid should become true at least once. So this should execute and the result should be reassigned at least once. The last time it's reassigned should be closest to the result. So our isValid function, now at this point, I'm just going to have a pointer I, and then I'm going to have our count, which is 0 initially. And we'll say while I is in bounds, we're going to check, is this number less than or equal to the capability that was passed into us? If it was, we can increment I by 2 and increment the count by 1. Otherwise, we will just increment the pointer by 1. And at the end, well, I guess inside the loop, we could check if the count ever equaled k. We could do an early break out of here. And then at the end, we can just return whether the count is actually equal to k or not. So this is the helper function where most of the logic went into. But you can see that this function itself is pretty easy, pretty simple once you know what to do. But assuming the rest of this code is correct, yep, you can see here that the code does work. It is pretty efficient. I can promise you that. So if you just want to see it one more time, here you go. But yeah, this is very much not easy to come up with. If this is your first time seeing this trick, this binary search trick on a problem like this one, it is expected that it's going to blow your mind. It definitely blew mine the first time I saw it. But thanks for watching. Check out Leetcode.io for more, and I'll see you soon.